flat disk. In this exercise, we consider a disk which is spinning in the space without gravity, and it has an inertia matrix, and this disk is totally flat. It is represented here, and there is several masses represented by green and black here, and they can slightly move. And the idea is to move these masses in order to control the disk. So the first question will be to find the state equation of this disk. The disk is represented here. It has an inertia matrix I, which is diagonal in its the disk frame. So we have A1, A2, A3, and all are positive because it is an inertia matrix. Moreover, the disk is totally flat, so it means that with respect to the first direction is with respect to x, I have the coefficient A1 is equal to A2 plus A3. So all of them are positive, and also I need to have this equality, otherwise I may have some masses along the x-axis, and in this case the disk is not considered as flat. So if the disk has a radius r, then the inertia matrix for a disk is known to be as follows. So m is the mass of the disk, and here I will have mass of the disk square, and the same here, and 0 and 0 everywhere. It is a classical inertia matrix for a disk. So as showed by this picture, the disk is able to spin around an axis, and the axis is named omega. So when omega is expressed in a word frame, I will write omega. If it is expressed in the body frame, I will write it omega r. So from this, the question is to find the state equation. So for this, I will assume that the orientation is given by the matrix R, and first question, since to find the state equation, I take into account the fact that the rotation momentum L is constant. So it is given by R, the orientation matrix of the body of the disk. Here I have I, the inertia matrix, and omega r, the rotation vector. So this one is constant. It means that L dot is equal to 0. As a consequence, I will have R dot I omega r plus R I dot, so if the inertia matrix can move, as it will be the case here, plus this one should be equal to 0. As a consequence, if I multiply everywhere by R transpose, so this will be equal to the identity because it is a rotation matrix. This one is equal also to the identity, and this one will correspond to omega r, this matrix. So this is a matrix, it is an operator which has the vector products this form a matrix. So as a consequence, if I isolate omega dot, this one, omega r dot, is equal to, I isolate this one, and I obtain I minus 1 multiplied by the derivative of the omega r minus omega r vector product e omega r. This one. Okay. So as a consequence, if I want to simulate this disk, I will consider as state equation the following. The derivative of r dot is equal to this. So this is a matrix. And omega dot or dot equal, and here I take the same as here. Now I know also that since I consider I as diagonal, then I consider that the following: 1 omega 1 dot is equal to this minus omega 2 omega 3 I2 omega dot 2 equal to omega 2 so this is a classical Euler equation. Now in my disk I have some masses where the distances are here L2, L2, which has to act in a symmetric way, so the center of gravity is not supposed to change. And here the distance will be L3, L3. So it means that in my inertia matrix, I will have to add here half of L2 square plus L3 square. So normally I have to multiply by the mass, but here I will consider that it is equal to 1, so the mass of the small masses, not the mass m of the disk. Here plus, and here I will have to add half of L2 square, and here half of L3 square. Now, due to this one, the derivative now, since this one is constant, but L2 and L3 can move with the masses. So I have here the derivative of A2 is equal to L2 multiplied by the derivative of L2, and the same for A3, L3 multiplied by L dot 3. Okay, now considering this one, I know that it is a disk and it is flat, so it means that A1 is equal to A2 plus A3. The same for the derivative, so I will not need to consider them. As a consequence, I will obtain the following, this one, the following state equation. So this one comes from the Euler equation, and this one, A dot 1, is just the one I have just proved just before. So now for simplicity, I will add some kind of small controller to make appear U1 and U2, just to simplify the equation I have here. You can consider that this one will be equivalent to U1 and this one will be equivalent to U2. So in this case, I will have some kind of bijection between U1, U2 and L2, L3. So I will control, of course, L2, L3 of the disk, but it is similar as if I control U1 and U2. Let us first simulate this system by a Python program just to check that it behaves like a real wheel. So I have the state equation I have just found before, and if I write this system with respect to U1, U2, I will obtain this state equation. Okay. First, I need a procedure to draw the wheel, the disk. So I need for this the rotation vector omega r, the inertia matrix I, and the orientation r of the wheel. I will also draw the angular momentum, which should remain constant normally, and I will draw an arrow in red to represent L, the angular momentum, given by this formula. Then I will compute L1, L2 with taking into account only the I matrix and also the one at rest with the 0 here, which represents the I2 bar in the exercise. I compute my rotation matrix in order to put the wheel at the right place. I draw here the masses, which depends on L2 and L3 at the right place. And I will draw the masses with respect to the second axis green and with respect to the third axis black. Okay, this is a procedure to draw the wheel. Then now, these state equations are given by this procedure, F, which depends on X, and U, the input. So for this, I will compute the variation for omega 1, omega 2, omega 3 here, which depends on the inertia matrix, and the evolution of E2 and 3, which depends on U1, U2, as given here. And recall that 1 is not needed since it is a flat disk. It should satisfy this equation. Now, once I have my evolution function f, I will perform a loop given here. So the initialization for omega, here it is the nominal matrix for I, which I have called before a bar, which depends on I1, 0, I2, 0, A3, 0. And since it is flat, I only need this one and this one. I mean this one and this one. Okay, so here in the loop, I form my state x, given the same as here, which depends on omega 2, omega 1, omega 2, omega 3, and the inertia coefficient, also given here. And in the loop, I extract omega r for the drawing here, and the orientation also. For the evolution, I will use a Runge-Kutta method to compute the evolution of the state x. Okay, and for the evolution of the orientation r, I consider the exponential integration scheme given here. So if I do this with my Python program, which is given here, the same I have just presented before, I run it, and I obtain here the disk moving. So the masses are not moving, they stay at the nominal place, and we can see here the angular momentum in red and the rotation vector omega, which turns around the red vector, the angular momentum. So in this case, in the case where they are not parallel, as it is the case here, we say that we have precession. Okay, so here we have a precision, and the idea will be to cancel this precision in the controller. Question number 2, we want to find a controller for our flat wheel, and for this we'll follow a Lyapunov control approach I will now explain. So for this we choose a positive, an objective function v of x which is positive, and such that v of x is equal to 0 when I am happy, I mean when the objective is reached. So v is a real number. And then this will help me to find an expression for the controller, which will compute u1 and u2. So recall that the state equation of my system is given here. Okay, this is my system, and the input of my system is u1 and u2. And to find a controller means to find an algorithm which will compute me u1 and u2 such that v of x will normally, I will try, converge to 0. So for this I compute an objective function v of x, where recall that x is equal to omega 1, omega 2, omega 3, and also e2 and e3. Okay. So the objective function depends only on x. It is positive, and when it is equal to 0, it means that the objective is reached. So for this, I will compute the derivative of v, and I will want that this derivative is negative, except of course when the objective will be reached. So we will see, we can understand that from this, v dot will be a function of x and of u. Okay. Because of course when I will derivate, I will make appear the derivative of the state, but they can be replaced by their expression, and u1 and u2 will appear. This is one. This one will have a form, this form, a of x multiplied by u plus b of x. So we can understand this. So in fact, what we usually do if we want to use a symbolic computation is to rewrite this one in what we call an affine form. So I mean the derivative will be omega dot 1, omega dot 2, omega dot 3, I dot 1, I dot 2. So I have rewritten this. I get this, where here I have u1 and u2, and I can recognize the correspondence between this and that. Here I have a dot 2. Okay, if I call this one f g1 and g2, then if this corresponds to an affine form, and I can write that v dot of x and u is equal to the Lie derivative of v of x with respect to f plus lg1 v of x multiplied by u2, u1 plus lg2 v of x multiplied by u2. So Lie derivative is a classical tool in control theory. You will not need it mandatory in this exercise, but if you want to use symbolic computation, it will be easier if you use this notion. But in fact, you can directly also make the correspondence between this and that. Okay, now we want to decrease v, this one. And it will recall that v of x is positive. So from this, will make a control strategy to find u1 and u2. Now I want to recall something, that this is linear, and if I want to decrease this one, so for a while I will call it this one A1 and A2. So if I want to minimize A1U1 plus A2U2, so they correspond to this. Subject to, so of course the minimum will be at the infinity, and I cannot move the masses of my wheel to infinity. So I will have to restrict and say, for instance, that U1 plus U2 should be equal to 1. If I solve this minimization problem, then I can see that U1, U2 should be collinear to the vector A1, A2. So it means that it should be equal to collinear, but in the other direction. So it should be something like -1 divided by the square root of, so the norm of the vector A1, A2, multiplied by A1, A2. So this gives me the controller I will use to decrease the objective function v. Question number 3, alignment control. So we want the disk spins around the first principal axis. For this, we choose the objective function that is given in the exercise. Okay. So the disk at the initialization is not spinning around x. It is spinning about something else. For instance, it is spinning around its second axis, for instance y. And I want it to rotate or to spin around the x-axis. So for this, I choose an objective function, which is this one. V of x equal to half, so half is not really needed, omega 2 square plus omega 3 square plus a2 minus a2 bar square plus i3 minus i3 bar square. So it means that when v of x is equal to 0, it means that v equals 0 implies omega 2 equals 0, omega 3 equals 0, and of course all the rotation will be transferred to omega 1. So it means that I will rotate around the first axis, around x. And moreover, when v will be equal to 0, I will have I2 equal I2 bar and I3 equal I3 bars. So it means that the masses will come back to the nominal value. So when v of x will be equal to 0, I will be happy, and the control will try to minimize the function, the objective function v of x. So for this, I can use, as explained before, the Lie derivative, but here I will try to do it by hand, just to show that it is not very difficult to do it, but it takes time. So it's better to use symbolic computation. So v dot of x is equal, so I will differentiate this one, and I will understand why I have this half here, because the derivative will be omega 2 dot plus omega 3 dot plus I2 minus I2 bar multiply by I2 dot plus I3 minus I3 bar multiplied by I3 dot. Now, due to this one corresponds to U1 and this one corresponds to U2. And we can understand that this one corresponds to this one and U1 will appear. The same for this one, which corresponds to this one, will make me appear U2. And at the end, I will have something which depends on X and on U. Okay. So if I compute this, I will obtain minus omega 2 square divided by I2 multiply plus I2 minus I2 bar multiplied by U1 plus minus omega 3 square divided by I3 plus I3 minus I3 bar multiplied by I2. And this corresponds to the Lie derivative with respect to G1 of V, and this one corresponds to the Lie derivative with respect to G2 of V. So for this function, it's quite easy to compute by hand, but most of the time it will be easier to use symbolic computation. And the other one will be cancelled out, so it means that in this particular case, the derivative of f with respect to v, in this case, it will be equal to 0. So it is why it does not appear here. So this one, I will not need it for the minimization. For the simulation, I will use here the symbolic computation. So first I build my symbols, omega 1, omega 2, and omega 3, and I2, I3. Here it is for the nominal value for the inertial coefficient. I build my system with the manifold of dimension 5 because I have 5 state variables. I build my coordinate function. F, G1 and G2 correspond to the one that have been obtained by this one. So recall that this one, and this one correspond to F, and this one correspond, and this one, the one here, corresponds to G1, and this one again, because of the U2, and this one here, and the one here for the U2 correspond to G2. So I build here my function f G1, G2. Then also I need to build my function v of x. So v of x depends on v0, which is this one, v0, which is built here. And I have to add this one, which corresponds to v2. So I have I compute here the Lie derivative that has been computed by hand. So in my specific example, the first Lie derivative of G1 will be given by this expression, and for L2 it will be given by this expression, but here it will be computed by the symbolic computation, by SymP. Then I will print them just to check that it is consistent with what I have obtained before. Then I will lambdify this function to transform into Python function that will be callable by my controller. So here it was an expression. This was expression, and now this one will become functions that are callable. So in my controller, of course, I will use this function, and recall that the controller was given by this formula, which corresponds to the minimization of the objective function with a restriction that the norm of the control is equal to 1. And this expression corresponds to this one. And it depends on A1, A2, which corresponds to the Lie derivative respect to the objective function. Okay, now I will perform my loop, where here I will call the control provided here, and I will integrate using the exponential integration chain and the Runge-Kutta as previously. If I do this in Python, so this corresponds to this same program I have just shown. If I do this, I run it, then I can see that at the beginning I start from rotating along the second axis, and slowly the precession is starting. You can see like that. And I will slowly have the rotate along my first axis. It was my objective. But if we continue the simulation for a long time, we will observe that the objective function will not converge to 0. I will still have some precession, which is not what I wanted. So we can see also in the simulation that the mass are moving. If I see my program, I see that indeed at the initialization I was rotating along the second axis due to this, and after, if I interpret the curve, I have a different here representation. First, I can see that the kinetic energy was decreased at the beginning because the masses went at the periphery of the disk. That's why it decreased at the beginning, and then after it increases. We can see that the objective function is decreasing, but will not converge exactly to 0. So there is some difference, which can be a problem. And if I see at the vector omega r, which omega 1, omega 2, omega 3, so at the beginning I see that I was rotating along the second axis, so omega 2 was equal to 10. And then after it decreased, slowly, but here I do not converge to 0. Okay, and omega 1 is increasing, which means that I am more and more rotating along the first axis, which was exactly what I wanted. So if I see in the plane omega 2, omega 3, I can see that I started from here, I was turning along the second axis, I moved like this, and slowly I converge to some kind of cycle, but I do not converge to 0, which is what I wanted. Now, in the inertial space, so I2, I3, I can see that I have some strange curve, which corresponds to my control. So at the beginning, the masses was here, so the inertia matrix, I2, I3 was equal to the nominal value. Then I moved to the right, which means that the second masses were escaping from the center, not the first one. And it's difficult to interpret why. Then I moved in this direction, and slowly the two masses came back to their nominal values. Question number 4, passivity control. So now we want to avoid the precession. So I want to have some kind of convergence. So the intuition we may have is to cancel the mechanical energy to transform into heat. So this is why I propose to take in my objective function the mechanical energy, which is composed of the kinetic energy and also the artificial potential energies that have already been considered before. So this quantity corresponds to the kinetic energy. And we want to find a controller to decrease v of x and also to illustrate by a simulation. So for the question number 4, the objective function is made with the kinetic energy given here that I want to decrease, and also some artificial potential energies that are inside my controller. So for this, I can compute v dot of x, it depends of x and u. I compute by hand, and I obtain this, but of course it's better to use symbolic computation to avoid errors. So we can see again that it all depends on u1 and u2, and then I will use my controller to decrease this function. If I do this, then I can see that, of course, u1 and u2 are chosen to decrease the kinetic energy. That cannot be cancelled because the momentum, the rotation momentum, remains constant, so I cannot cancel totally my kinetic energy without using external forces. So the objective function decreases because it is also proportional to the kinetic energy, so it's everything is normal. We can see also that the precession still exists, and this is quite surprising, but not totally, because I have my flatness condition, which asks me that E1 equal A2 plus E3. It means that I am not allowed to move the masses with respect to the first axis. And due to this, I am not able to decrease the kinetic energy as much as I want. So it means that it's not a good way to decrease the precession. I should be able to do better, even if I have my flatness condition. I can see again that in the omega 2, omega 3 space, I do not converge to 0. And also what happened is that I converge to something like this, but the potential energy, I am not able to come back to 0, I mean to the nominal value for my initial, for my inertial coefficient. So the conclusion of this is that probably the kinetic and decrease the kinetic energy of the mechanical energy is probably not a good idea when I have a flat wheel. I could be able to do something better. Okay. So for this, it is the question number 6. I will try directly to decrease the precession. And the precession is given by this, and I will explain why. The objective function is given here, and we can see that we still have the potential energy, but this term can be understood from the Euler formula. So it corresponds to the norm of this vector. Because when I don't move the mass, the inertia matrix does not move, so it means that this term, and this term are all equal to 0. So when the objective function is reached, it means that this is equal to 0 due to this, and then I will have no more evolution of my rotation vector, and it corresponds to the fact that I do not have any precession. So if this one is equal to 0, I have no more precession. So it's a motivation to use this one. So of course I will use SIMP. I take this one as an objective function, and a symbolic computation give me this. So it is quite heavy to do it by hand. This is why the Lie derivatives are very useful here. If I do this, I can observe that, of course, the kinetic energy have some kind of behavior like this and converge to a given value. So it decreases because the masses go to the periphery of the disk, but after they come back. Okay, this is what it increases after. The objective function decreases and converge to 0. Omega 1. So converge to a value, and we can see that the other value for omega 2, omega 3 for a given initial condition where I have some precession, then I will converge to omega 2, omega 3 equal to 0. So it means that I converge to some place where I do not have any precession. I cannot control the principal axis toward which I will converge, but this objective function makes me avoid any precession. I can see here in the omega 2, omega 3 space that indeed I converge slowly to 0, and here it is in my input space. So now the idea of the last question is to combine different strategies in order to switch from one rotation along one of the axis. Here it is the second axis, and I want to find the control strategy so that we spin around the first axis and not the second axis. So for this, of course, I will combine the first controller, which make me be near the desired rotation, and the last controller, which makes me avoid any precession and which may be attracted by one of the principal axes. So first I will have to go near to the first rotation along the first axis, and then to converge to it. I obtain the following curve. So we can see that at time t equals 0, I rotate, so my disk rotates around its second axis, and the first axis is like this. So I'm here, rotate the second axis, so omega 2 will decrease and will slowly decrease like this. And then after, of course, I will switch to the so this one corresponds to the first controller, and this one to the second controller. Then I will change the strategy and cancel the precession. So here it is a precession controller, where here it is an alignment controller. So I try to align, and then after I finish the job by using the precession controller. So here we can see that the objective function decreases, and here I change the objective function because I take into account the precession, and then I will be able to improve the result. So at the end we can see that omega 1 increases and will converge to some value, so I will rotate around the first axis and not anymore with respect to the second axis. It was the objective. In the omega 2, omega 3 space, I can see that I start from here, I converge to here. So here I was rotating around the second one, and here around the first one. And here it is the inertial space, just difficult to interpret.